Hi everyone. This part of our educational course is on brain network analysis, theory, and interpretation. My name is Shella Kyle-Holtz, and I'm going to be walking you through kind of an overview of how you might use network analysis in functional neuroimaging. We don't have a lot of time, so I'm hoping just to give you a feel for some of the tools that are out there and some of the analysis that's available. So you'll find online that there is an assignment posted along with this presentation. You can do it or not do it as you like. But if you do it, it will help you make the graphs that I show and the figures that I show in this presentation. And so you'll note that some of the slides have numbers at the top, and those are pointing you toward the corresponding sections of that assignment so that you can make the graph shown on that page. So for this lecture, I'm assuming that we've already acquired our functional brain imaging data. We've done the pre-processing. It's perfect. It looks beautiful. And then it has been parcellated using your favorite parcellation scheme. And then you've calculated functional connectivity pairwise between every pair of parcels. So we're going to start with this graph on the right, which you can call a functional connectivity matrix. And this can represent correlation or some other measurement between pairwise parcels in the brain. Okay, so let's talk about this functional connectivity matrix. I'm going to be using the one that comes with the brain connectivity a toolbox, and that was described in Crossley et al. PNAS 2013. So if you open this data that they include with the toolbox, you'll get a plot like the one that I'm showing you over here on the left. And in this matrix, the correlation values have already been Fisher transformed, and the matrix has been thresholded. And so, you can see looking at the color bar that a lot of these connections are set to 0 because of the thresholding. So some questions to ask yourself about the matrix. First of all, is this matrix symmetric or asymmetric? Because we are using functional connectivity, everything in this bottom left triangle is going to be mirrored about the diagonal to the upper right triangle. So this is a symmetric matrix. It could be asymmetric, for example, if we were looking at effective connectivity or something that gives you a directional measurement. Similarly, we want to ask whether this is a directed or undirected matrix. Functional connectivity based on correlation doesn't tell you anything about which way the connection between two areas goes. So this is an undirected matrix. And then we can ask whether it's weighted or binary. The values vary between 0 and my color bar says 1.6, and they're not just 0 or 1. So this is a weighted matrix. Later, we're going to threshold it and make it a binary matrix. And then there's this question, are self-connections included? And we ask that because some of the analysis methods that we use, actually, in fact, all of them, I think, for this toolbox, assume that you have eliminated self-connections. And what I mean by self-connections are the functional connectivity between a parcel and itself, which is always going to be 1 because they're perfectly correlated. To determine if there are self-connections, what I've done here is I've zoomed in on that diagonal of the previous functional connectivity matrix. And now you can see along the diagonal, there are a row of zeros, which shows us that self-connections have already been zeroed out, which is perfect. Okay, I also wanted to know what the matrix was thresholded at. That wasn't in the data that I saw. So I made a histogram from the functional connectivity matrix. Most of the values that have been eliminated are 0, of course, but what I'm interested in is what this number is where we start to see the higher values again. So again, it looks like they have thresholded this at 0.6 so that everything below that is 0, and only connections that are stronger than 0.6 are still in this matrix. Okay, so something that we are interested in when we talk about comparing different networks is the density. which is the total number of connections that are present over the total possible number of connections. So if I just find the number of non-zero matrix entries in my functional connectivity matrix, I get 37,250. Now I know that I have 638 parcels for this particular data set. So my total number of possible connections is 638 times 638. And so my density here is 0.09. And this is important for comparing networks because you want to look at networks that are of similar densities, and you'll see how that affects our. Once we have a network, we can also start to characterize some of the particular nodes in the network. So I'm showing here over on the left a toy network that I'm going to use just as an example for a lot of the measures that I talk about today. So each of these circles is a node or brain area. Each of the edges is between it, tells you what it's connected to at a given threshold. For now, I'm going to use just an unweighted, undirected network, but a lot of these features are generalizable to other types of networks as well. So the first thing we can talk about is degree, and that's the number of links connected to each node. So for example, if we look at this node, the degree is 3 because it has 3 connections. Whereas if we look at this kind of lonely node here, its degree is 1. And if we look at this node that seems to be kind of centrally located, its degree is 5. Okay, now if my network is also weighted and not just binary, I can calculate the strength of the network the strength for each node as well, which is the sum of the weights of the links that are connected to that node in the network. So here I've made a very simple weighted network where the weight is either 1 or 2, depending on whether it is a skinny line or a thin line. And so if we look at those same nodes again, this one now is 2, 4, 5 is the strength. This one is still 1. And this middle one now is 1, 2, 3, 4, 5, 6. Okay. If you plot, now I'm looking at the degree and strength for the functional connectivity matrix that we're using with the Brain Connectivity Workshop toolbox. If I plot the degree and strength, you'll see that they're quite similar. So that if a particular parcel, as shown here on the bottom axis, the x-axis, for each parcel I'm plotting degree in blue, strength in red, and you can see that these are very correlated, right? Voxels that are parcels that have a high degree tend to also have a high strength, which makes sense because they're both kind of based on the number of links coming in. Now you can also visualize these networks. So for example, this is that functional connectivity matrix thresholded and then plotted in 3D space, and you can see where the connections are thickest. For example, here between left and right areas in the brain, here back in the visual cortex. So this is just another tool that's available, and I wanted to show you that you can take these matrices and put them back into something that looks like brain space. Now I want to go back to our toy network again, and I think it should be obvious by looking at this that there are important features of structure that really aren't captured on a node level measure of degree, for example. So we want to be able to say something about how this network is put together. And there are several options that we have available for this. So the first one I'm going to talk about is the clustering coefficient. And this is just the fraction of a node's neighbors that are neighbors of each other, divided by the total number of the node's neighbors. So let me take a look, let's say, at this node right here. So the number of neighbors it has, it's got 3 neighbors, here, here, and here. And each of those neighbors is connected to the other 2 neighbors. So it has 3 neighbors, and they're all neighbors of each other. So 3 over 3 is a clustering coefficient of 1. Now maybe I take a look over here at this triangle group. So now I'm going to look at this node. Actually, I'm going to come back to that node. I'm going to look at this node. And this node has 2 neighbors. Both neighbors are neighbors of each other, so also a clustering coefficient of 1. But now if we look at this node in between groups, this node has 3 neighbors, but only 2 are neighbors of each other. So its clustering coefficient is going to be 2/3. And so this is a property we can calculate on a node-by-node basis, but it does give us some information about how the nodes in that graph are grouped. Here is an example on this data that was presented with the brain connectivity toolbox again. So first I'm showing 2 different thresholded matrices. So these are now binarized. In the first case, everything above 0.6 was set to 1, everything else to 0. In the second case, everything above 0.8 to 1, everything else to 0. And so you can see over here that the graph is much more sparse and we have fewer connections. And I did that because now that we're looking at network structure, I think it's very informative to look at the influence that the density of the graph has on these metrics. So if we look at the clustering coefficient per parcel, this is over on the left for a threshold of 0.6, we can see that it ranges from 0 to 1, and that the mean is about 0.55. If we go to the graph with the higher threshold, we see a lot more low values. And again, the overall mean is reduced because of those low values to 0.43. So clustering tends to go down as you make your graph less dense and you remove some of those links. So I just thought I would show this for interest. We showed strength versus degree before we plotted those together, and they looked highly correlated. If we plot them against each other, you can see that this is the case. This is practically a linear relationship over here on the left. Well, clustering coefficient gives you something different. So if you plot that versus degree, you can see it's much more scattered. And so this is telling us something that's not the same information that we were getting before. So what are other ways that we can describe the network structure? Well, if I look at this, I might say, wow, these nodes are kind of all connected together, and these nodes are all kind of connected together. And so maybe there's a measure that we can come up with for that. And that is something we call modularity. And there are different algorithms that can be used to calculate modularity or assign nodes to different modules. But they all try to maximize the number of edges within the modules while minimizing the number between module edges. And so I think probably the solution I'm going to draw here is a pretty good one. You know what to do with these? Not quite sure. Maybe this node should go here? Probably not. Okay, but one of the things about modularity is because there are algorithms to calculate it, different algorithms will give you different results, and usually there's a random initialization that also changes your results somewhat from run to run. So here I'm going to show modularity for 2 different runs. This is on the 0.6 thresholded functional connectivity matrix. So we've got parcel number across the bottom and the module assignment as the vertical axis. And you can see in the first case, the algorithm came up with 9 modules. In the second case, it came up with 10. And this looks really messy and really crazy and different. But if you actually look at how many main modules are detected, that's fairly reasonable across the 2 runs. So in the first run, you see maybe 1, 2, 3, 4 fairly large modules, and the same in the second run. And so, you know, you need to do some sort of management of robustness of this sort of algorithm, maybe running it many times and taking the consensus result or something like that. So if you plot these modules back on the brain, this is from that original PNAS paper. I just wanted to kind of show you what they look like. Here you can see, you know, you've got clearly this yellow module that's visual cortex, something green kind of down the middle. And then these red and blue modules are spatially distributed, but very close functionally. So you can go back again to plotting these out on the brain. Okay, so I told you I wanted to look at the effects of threshold and density on network structure. So here again is a run for the modularity on a graph with thresholded at 0.6. And on the right-hand side is the same thing for a graph thresholded at 0.8. And you can see that the number of modules has gone up substantially because you've been eliminating some of those weaker links, and so you have less connections overall and you get more kind of tightly connected clusters. But we've gone from 10 modules to close to 70. Okay, well, how else could we describe network structure? One idea is to think about it in distance. So if you pick a node, say this node, and you want to get to another node, say that node, you have to figure out what the shortest number of edges is between those two nodes. And so here it's 1, 2, 3 edges. Now I can get there many other ways, right? I could also go this pathway and make it long and complicated, but the shortest path should be a unique number. So we call that shortest path the distance. And so for every pair of nodes, we can create a matrix that tells us the shortest path between one parcel and another parcel. And that is shown here on the left for the graph thresholded at 0.6. If you look at the color bar, you can see that the maximum path length between any two parcels is 8 for this graph. And again, this is symmetric, and so all of the information is really contained in either the top half or the bottom half of the graph. Now, if we threshold the graph at 0.8 before we measure distance, the maximum path length goes up because, again, you've eliminated those weaker links that might give you shortcuts and you have to go the long way around. So you can calculate a characteristic path length by doing the average of the overall path length. So you can see here, this is again for the 0.6 threshold. I've plotted the distance for all as a histogram for all the different pairs of parcels. You can see most of them fall around 2 or 3. So our characteristic path length, it's going to be in here somewhere. And then our global efficiency is just going to be 1 over that characteristic path length. And that global efficiency tells you something about how easy it is to move about this graph and how easily information can be transferred around that network. So our efficiency for a graph thresholded at 0.6 is 0.44. If we make the threshold 0.8, remember our path length gets longer because we lose those weak connections, and our efficiency goes down. I want to talk about one last way to describe the network structure, and that's in terms of betweenness centrality, which tells us about how central a node is to all of the shortest paths between many other nodes. So if you're traveling from one node to another, let's say node A to node B, how likely are you to go through node C if you're taking the shortest path? And so these nodes a lot of times are nodes that connect different modules, for example. So this node is going to be in the shortest path for this node and this node to get to all of these nodes over here. This one is also probably going to have high betweenness centrality because you can see that it connects these other nodes in its module with this module. So we can look at betweenness centrality again for our two graphs at different thresholds. And so you can see for either threshold, there are some nodes that have very high betweenness centrality relative to the others. And like I said, those might be in important positions to help transfer information. And we can also overlay these, and you can see that the betweenness centrality does depend on the network structure. And for example, here you can see a node that is high on betweenness centrality at one threshold, but not at the other. And again, this is because of the restructuring of those paths. Okay, well, I'm almost out of time, and there's a lot of things that I didn't cover. We didn't talk about rich club coefficients, local efficiency, eigenvector centrality, but luckily there's a lot of great documentation for the brain connectivity toolbox, and you can go to the site and kind of check out what you've missed and try it out on different data. I just want to really briefly mention the problem of null models. So let's say you want to make a statement, something about the modularity of the brain. Well, how do you decide if that modularity is important? So you need to find some way to say whether that modularity is something that you would expect by chance. Now, depending on the question you're asking, you might have to be very careful about how you make your network structure. And so sometimes people take the approach of, randomizing actual networks by just kind of randomly switching connections to try to preserve certain characteristics like the degree distribution or the average path length. You can make generative models that ensure features like small worldness, for example. But there's not really a one-size-fits-all approach, and I encourage you to look at the literature on this. There are a lot of groups doing active research in this area, and they've got some great tools. And the last thing that I wanted to say is don't forget, we've started with this functional connectivity matrix, but when we're drawing conclusions, it's all about the data. If you have noise that makes functional connectivity, unnaturally high, if you have some sort of loss of SNR, maybe due to a loss of vascular elasticity or something that changes the SNR and changes the overall correlation in your graphs, those things are going to show up when you do network analysis. And so a loss of SNR, might mean that you have overall weaker links. It could give you a less dense graph at a given threshold, or it could affect things like your modularity or your efficiency. So just keep in mind the underlying data when you're trying to interpret your graph theory metrics. Okay, I'm already over. I've got to stop, but I'd be happy to answer questions or take comments during the Q&A period.